now let me state the Poincaré duality theorem, or one of several Poincaré duality theorems we'll consider. So if we take a closed R-orientable manifold of dimension m, so in particular there exists a fundamental class. Let's denote that in the standard way by m in square brackets. Then the theorem states that taking the cat product with the fundamental class gives an isomorphism between cohomology and homology m minus star with R coefficients. This is an isomorphism. So by the previous remarks, we know that any manifold has Z mod 2 Poincaré duality. Okay. Now, section 2, we'll talk a little bit about local coefficients, which we've implicitly been talking about already. So what are local coefficients? Well, local coefficients are a tool to organize information about the action of the fundamental group. On various other abelian groups, which we then consider as modules over the group ring. Using local coefficients, we get a fundamental class for non-orientable manifolds. So for example, like we did with Z mod 2, and thus this gives a way to extend Z coefficient Poincaré duality. And there are two equivalent point of views to take. There's a more algebraic point of view and a more geometric point of view. So, firstly, you can say the main chain complex of interest for any manifold M is that of the universal cover. Where we view the chain complex of the universal cover as a Z pi 1 module chain complex. Where the action of pi 1 is the standard action by deck transformations. So pi 1 module chain complex. And then, from this point of view, local coefficients are simply modules over the group ring. And in the second point of view, slightly more topological, we think of fiber bundles over M with abelian group fibers. So for example, when we were thinking of M sub Z, all the fibers over the points were the abelian group Z, or MZ mod 2, the double cover. Fibers with abelian group fibers, so the abelian group G here, and the transition functions in the automorphisms of G. And then this gives us a chain complex of formal sums of singular, or as I was thinking with the wherever the simplicial example's gone, you can do this with simplicial complexes or cell CW complexes. A formal sum of singular simplices with coefficients in the fiber over that simplex. So, just like in this example. Now that we're going to be considering the group ring, it's worth making the remark that pi 1 may not be commutative, so we'll have to distinguish between left and right Z pi 1 modules. Pi 1 need not be commutative, so left modules not necessarily equal to right modules. So we have to distinguish. Between the two. But we can switch. If we have a left module and we want to think of it as a right module, we can switch between the two via acting by G on the left being defined to be acting by G inverse on the right, or vice versa. So let's see, it's probably almost time for a break. Almost. So the first observation, which I've already said, is that the chain complex of the universal cover, this can be considered as, so in this talk I'll consider it as a right Z pi 1 module. Chain complex, either for singular or singular simplices or cellular chains. Again, pi 1 acts by deck transformations, and we extend linearly to Z pi 1. So just before we take a break, I'll give one example of considering the chain complex of the universal cover as a Z pi 1 chain complex. So again, we'll take more or less as simple an example as we can do. Take S1, the universal cover is the real line. Let's think about cellular chains. So we'll give S1 the decomposition with a single point and a one cell. This induces a decomposition for the universal cover, which is a 0 cell at each integer point and a 1 cell between each integer point. I'm going to call this loop E. I'm going to call the generator of pi 1 that goes around this way T, and I'm going to call the 0 cell X. So we choose a lift of our point X and a lift of E to the universal cover. So here's X tilde, here's E tilde, and then we label all the translates using T, the action of the fundamental group. So if T was going to the right, this would be, well, I'm thinking of it as a right module, so it should be xt, and this is et, this is xt squared, etc. Xt inverse. And you label the entire line like this. And then, so, C1 of R is the group ring. This is Z pi 1. Z of Z we can write like this and think of it as Laurent polynomials. And this is generated by our lifted cell E tilde. We have a boundary map. What does the boundary map do? We take E tilde, we get plus the point to the right and minus the point to the left. So this is T minus 1 as the boundary map. And then this maps to the group ring generating, well, single generator X tilde. And so this is the chain complex of the universal cover, considered as a Z pi 1 module chain complex. Okay, and that's a good place for a break.